Hi, so today I'm going to be going over an 820-2936 board that does not turn on. So here we have the board, and the issue with it is that you will get a green light on the charger, but it does not actually turn on. So let's plug it in so I can show you. So as you can see, I have a green light, but my fan is not spinning. So we have to troubleshoot what's going on here. So now, one of the things I've shown you in prior videos is that one of the beautiful things that you'll find in the schematic is that on the beginning of the schematic, you'll see a list of power rails that should be present. So you don't actually have to work and guess to see what should and should not be present. You can simply look at it, and it will give you a nice little list. Well, when I say nice, I'm being a little bit of a troll, because as you can see, it's kind of long. So you have all these rails from top to bottom here, and let's point and show you. So you have PP bus G3 hot, which is the 12 volt rail that the machine runs off of. So let's measure that. I'm going to measure that in the multimeter. I'll lower this so you can see the meter a little bit, even though it's probably still invisible. It'll be hidden behind a Poland Spring bottle. So over here, I've got, you know what, let me do this. This is backlit, so you can actually see it. And the board view will tell you what these points are. So if I want to measure PP bus G3 hot, what I can do is I can go to the board view software that I have open over here. I can click N, type PP bus underscore G3 hot, hit OK. It will zoom me out because it's a piece of shit, and then it will show me all the points on the board along which PP bus G3 hot shows up. So one of the places it shows up is this big white fuse over here, so I'm going to measure. And I see on the oscilloscope, I see 12.7 volts. See how it just jumped there? That's a jump into 12.7. I don't feel like zooming in. I figure you can trust me when I say that it's 12.7. The next power rail here is one that is dragged from PP bus G3 hot, so I'm not going to bother testing that. PP bus S5 HS computing iSense. I don't care about that because that is actually drawn from PP bus G3 hot. Same for this. Then we have PP bus PPDCAN underscore G3 hot. That's the 18.5 volt rail of the machine. That's the 18.5 volt rail that comes from the charger. Now the charger gives the board power to create PP bus G3 hot. So if I already have PP bus G3 hot, why do I care about this DCN power rail? I don't. PP3V42 I know I have. As I've explained in other videos how the one-wire circuit works, the one-wire circuit has a logic gate in it that is powered off of PP3V42. So if I have a green light in my charger, obviously I have that, so checking that is pointless. PPVRTC underscore G3 hot, that is a different supply. I'm not really interested in seeing if I have clock signal yet because it doesn't turn on. Even if I did not have clock, I'd at least see the fan spin, it would spin and then it would turn off. RTC is one of the clocks in the machine that synchronizes the, everything so that it knows what to do and turns on and it does, works. When I say turns on, I don't mean turns on like actually fan spins, I mean, CPU, PCH, all that good stuff. Next is PP5VS5. Let's see if I have PP5VS5. I hit N over here, PP5V underscore S5. And where does it show up? PP5VS5 shows up over here on the main board. So right next to U7200. So I touch the oscilloscope probe over here to that part of the board, and I see 5 volts. Okay, so all the power supplies are checking out so far. Let's check the next one. Next one is PP5VS3. So let's check PP5VS3. I check PP5V underscore S3. And what do I have here? So let's bring it to this side of the board. This is a point where I can check it. Let's see. I can check that power supply right here. So when I plug this oscilloscope test lead here to check for PP5VS3, I get 0. See, now I'm interested, because one of the rails is missing. Now the 5 volt rail is one of the rails that you need in order for the thing to turn on. So PP5VS3 will get turned into PP5VSO, S3 means it's present when the machine is off or sleeping or something or hibernating or whatever. And SO means that rail is present when the machine itself is actually on. So there is something on the machine that says when you plug this in, when you plug the MagSafe in, and when you are turning the machine on, turn PP5ES3 and a PP5ESO. Let whatever is present at PP5ES3 flow to PP5ESO to turn the machine on. And that's not present here. So one of the things I want to do first, before I actually start fucking with it, is see if there is a short to ground on that power rail. So I'm putting my multimeter in diode mode because it gives me very, very quick measurements. I'm going to put my red probe on ground and my black probe here, right where I tried to measure for PP5ES3. What I have here is not a short to ground at all. I have a fairly healthy reading, so I'm getting a very, very, let's see, I'm getting a very high voltage drop to ground. So now what I'm interested in is seeing, will this thing actually turn on if I just put 5 volts there? So what I'm going to do right now is put 5 volts there using this HP Agilent power supply that I got. So watch what I do here. So I'm just going to make a space to solder my ground wire here. I am going to put some solder on that little space, and then I'm going to put the wires. So this here is a bench power supply. It's a Hewlett-Packard 6542A. It is old, probably older than me. It is old shit, but it is good old shit. It is a linear power supply, which is very inefficient. However, even though it is inefficient, it is a linear supply with very, very low ripples. So you can use it for powering. It's very, very accurate. So when you say, I want 5.002 volts, it will give you 5.002 volts, which is cool if you're a nerd or you want to use it to power cool things or audio circuits or things where ripple actually matters. But I mainly got it because it was $120 and I needed a bench power supply, and if I want to buy a new bench power supply for $150, you will get something that is kind of a piece of shit. Whereas if I'm willing to buy used and wait for a while, I got this. I got this to replace my Lenovo, which finally hit the bucket. So what I'm going to do here is I'm going to set my bench power supply. I'm going to set the voltage to it to 5 volts, and then I'm going to set the maximum current to 2 amps, because there's really no reason to provide more than 2 amps to this shit. If it does, that means there's a short of some kind, and I don't want to blow things up. So what I'm going to do is I'm going to plug this in, and then as soon as I plug it in and I see the light turn green, I'm going to turn the power on this bench power supply, and I want to see if it turns on. Blah. And it did turn on. So you can see here, remember these Core i5, i7 boards actually do turn on their own. And as you can see, I have a spinning fan. And as you can also see on the bench power supply here, you probably can't because it's covered by a clusterfuck of wires and numerous pole and spring bottles, is that my power supply is delivering 4.999 volts at 0.18 amps, which means it is actually delivering power to the 5-volt rail. It is doing something. Now, one of the things I want to do is actually check out why that shit ain't working. So I know that I've gotten somewhere. I know that if I have power on that line, that, you know, the computer's not going to blow up, that it is okay. So I'm going to just remove that wire that I put there. And let's take a look under the microscope to get a closer look, a better idea of what is going on. Let me turn this off. And also let me show you on the schematic what we're looking at. I'm using the wrong soldering iron tip for this. This is a micro tip that I'm using to remove a huge blob that I made. Alrighty. Oh, into the microscope we go. So, first things first, actually before the microscope, is schematic. Let's get a little bit of learning done here. So the power supply that is missing is PP5ES3. So let's see what PP5ES3 is for, what it does, and man, I really need to get a camera person for this. Alright, so PP5E_S3. Come on. Show me where you're made from. Okay, well I'm going to cheat because I already know where it's made from and I want to save time. I'm going to search for that chip. Okay, so this is the chip that makes PP5ES3. Now to explain a little bit of how this thing works. There is an N-trip signal over here that when you go to turn the machine on goes up to 3 volts. If that signal is allowed to go up to 3 volts for a second, it will actually turn the rail on. But if that is not allowed to go up, it won't turn it on. So you have a little transistor down here that will actually take that and send it straight to ground, right over here, depending on what the PCH or the MCP tells the computer that it ought to do. You also have other things here that are important to know about. So this fucking PDF reader. So this chip controls this buck regulator here. This buck regulator takes 12-volt pulses. It makes a bunch of 12-volt pulses and sends those 12-volt pulses to the input of this inductor, where those 12-volt pulses then turn into 5 volts for the machine. Once we get this working, I'll show you what the input and the output look like. So this chip, this U7200, which is TPS 51125, this chip right here, it controls these 2 transistors, which then make power for that inductor, which then gets smoothed out into a nice 5 volts and moves on. So one of the things that I like to do when I find a problem is try to find a story. I like to try to follow a story. I like to follow science, but I also like to see why it actually happened. So there's the science, and then there's a real-world application of the science. So let's try to get a look here and see what's going on. So I'm going to go into the microscope, and I'm going to look at this chip, and I'm going to try to get an idea of what exactly happened and in what order it happened so I know what to do. So this here is my TPS 51125. And this is the chip, and as you can see over here, there is a red probe point. This is the kind of thing that I want. I want to see that, and I want you to look at that and have an innate understanding of what went on in the circuit as soon as you see that. So I want you to have an idea of how the electricity passed through the circuit. I want you to have an idea of bing, exactly what it is that happened in order for the destruction to occur. And that's something that you're going to get with experience. But it's also something that you're going to get just by looking at the board. So that little, every time you see those red probe points, it's usually indicative of water damage of some kind that landed there, and there's something going through that wasn't supposed to. So let's get a look at the board view and see what that's supposed to be. So that probe point is... I really need a joystick for this thing. I need to make a joystick for this board view software, because it is so goddamn frustrating sometimes to use with... Okay, so over here we have, this is the probe point that I'm talking about right here, and that is P5VS3 underscore VBST underscore R. So now I'm going to open up the schematic. Before I open up the schematic, P5VS3 underscore VBST underscore R. I want to see every point that this shows up on this board, and of course when I do that it zooms me out completely so that I can't see shit, because that is how this crappy software works. It is what it is. It hasn't been updated since 1995. So that probe point, you have this capacitor and this resistor right next to it. So C7260 and R7260. So let's see what those look like over here on the schematic. So R7260. So that is a resistor that goes from, here we go. So we have the output of this buck regulator. So this buck regulator over here is going to take the 12-volt pulses from the PP bus G3 hot rail. It's going to make pulses that go through the inductor, and it's pretty much what the inductor is going to do. It's going to take those pulses of 12.6 and 0, 12.6 and 0, 12.6 and 0, and it's going to smooth it out, and it's going to average it into what is going to become 5 volts. So what this does, that little resistor, it sends a signal back to the U7200 to pretty much let it know what those pulses are doing. So let's see what that resistor looks like. So I'm going to put my multimeter back into resistance mode to measure resistance, and I'm going to check for R7260, and I want you to pay attention and tell me what it is you see, because hopefully we have found the cause of a problem. Wouldn't that be cool? So R7260 is located right over here, and when I look at R7260 and I put the probes of the multimeter to it to measure it, instead of getting 0 ohms, I get OL, which is more ohms than I want. So let's try replacing that with a resistor from a donor board. We're going to take a donor board that's just like the board that I have here, and I'm going to look at that resistor on a donor board, and I'm going to measure its resistance, just to make sure my multimeter is not broken, just to make sure I haven't lost my mind. And let's see what I get. So here is on a donor board, which I've already apparently stolen a bunch of stuff from. What can I say? and I get 0 ohms. So this tells me that I have found the potential cause of my problem. So let's continue on to replace that resistor and see what happens and see if we get a working board out of this, because there is a good chance at this point that we can get a working board by simply replacing a simple resistor. Wouldn't that be cool if we didn't have to do a lot of work and a lot of misery? Alrighty, so we're going to take that resistor right here. Goodbye. Oh boy. And I'm going to take some solder. I'm going to make sure that I'm not running out of disk space. I almost forgot to check and see that I'm not running out of disk space. That would be smart because I am doing a video in real time. I have 325 gigabytes left, so I'm good. Now I have 324. Now I have 323. Wow. Alright, so doing 2 raw video X264 streams in real time is, yeah, something else. That's 60 frames a second. So we just put a little mic. Alrighty. And we're going to take a resistor off of here. Also, if enough power went through that resistor to blow it, there's a good chance that my chip is blown up as well. So I might as well replace the chip. But I'm curious to see if this on its own solves my issue. So let's see what happens. I'm going to plug this in. Okay, and let's see if I got some fan turning on. Okay, so as you can see, my fan is now spinning. And as we like to joke here, because there are many outsourced repair centers that will actually, this is their testing, we are done. No, seriously, we have a running joke here, because there are a couple of outsourced repair centers whose name I'm not going to mention, who they say that they test every board before they send it back, but they see the fan spin, and they're done. And honestly, I've started to understand why that is, because you think you've got it, and you've solved this problem, and it's like, oh, I'm at the top of how I could possibly feel. I couldn't possibly feel any better than how I feel right now. So why ruin it by plugging a screen in and seeing that, you know, there's no CPU vCore, that it doesn't work? Why ruin this beautiful moment by seeing that it works? But no, unfortunately, I do provide service to a decent standard of quality, which means that I have to actually make sure this thing works before I send it back to the customer. Which means that, yeah, I can't just say that I'm done because I saw the fan spin. But that would be cool, wouldn't it? Oh boy, that would be cool if I was done right now. So again, this is the importance of using your brain. This is the importance of science. This is the importance of combining science with the basic know-how of just looking at things to get an idea of what's going on. Because so many people are going to say, replace the chip that makes that voltage. The chip wasn't bad. The chip was fine. There's no reason to replace the chip. Absolutely no reason to replace the chip when the chip is clearly good. So, alrighty, so I have the screen turning on, which means my CPU must be good. And once I get that question mark folder, I will be happy. Now, I'm not going to run ASD and do all that stuff on camera, because frankly that is just a complete and utter waste of bandwidth and video. And as you all know who are watching this series, I do use Time Warner cable to upload these videos, which means that this video, if I make it any longer than it is right now, will take literally days to upload to YouTube, including all the drops and garbage that you get when you pay Time Warner business class cable $175 a month for an internet connection that is worse than the 56K modem that I had when I was 12 years old. So let's see. Okay, as you can see, I have a flashing question mark folder, which means obviously most of my functions of my machine are good. Again, we could have issues with current sensing, we could have issues with other things, but this thing came in totally dead, and now it's working. So now I can put it in the bin of machines that need testing to make sure that all functionality is okay, and I can take it out of the bin of quote-unquote completely fucked boards that are sitting on my desk. So hopefully you learned something from this. Hopefully you learned my troubleshooting process a little bit, just a little bit of what I go through to figure out what's wrong with the board. Again, I did not do anything to make this look easier than it is. I did not start working on it. I did not start soldering on it. I did not start doing preliminary diagnostics before I turned the camera on. All of this was done in real time to show you just how simple it can be when you have the right mindset, when you're thinking in the right way, when you're thinking analytically, and when you have the right tools in front of you, and when you have the willingness to learn.